Alright, chapter 12. So, there's really nothing new in terms of concepts that are being introduced in this chapter, but the application of those concepts will be sort of new, or maybe more correctly, you're going to take applications of concepts that you've used before, use them in the same way, but combine them in a bit more complicated ways to get to a solution. And so this chapter is about equilibrium. In other words, that means you have objects that have mass and are like different shapes. So um, you'll need to consider that the mass of extended objects like a beam or a box or something like that, and they are in equilibrium, so they're not moving. So in other words, everything must be balanced out in equilibrium. So that means forces must be balanced and torques must be balanced. That's really it. But applying it to problems can be tricky. So you notice I have two net forces, net force X and net force Y. You don't always need both of these. For example, in this picture, you can see all the forces are only in the y direction, so you wouldn't need a net force X equation for this. But in this one, you can see on the beam you have a tension pulling down. That's tension from the rope. That's in the y direction. You have a tension from the cable. That's TC. That's in the x direction. You have a hinge pulling up on this beam, preventing it from falling down. So that's a y direction force. And you have the wall, which is connected to the hinge. So technically the hinge is pushing this beam that way. And so that's an x direction force. And don't forget, you have the weight of the beam, because this is not a massless object, and that gravity is always in the y direction. So essentially what you do is you just create a net force equation. So for example, for this one you'd have F net Y equals 0, because it's in equilibrium, so those forces all cancel out, and that's going to equal, we'll call up positive, down negative. So 20 is up and F2 is up, so plus F2 minus 10 minus F1 and minus 30. And we could also do a net torque on this. And the thing about torques is, first off, it's not up or down that is positive or negative. It's clockwise and counterclockwise that's positive or negative. I usually call clockwise positive and counterclockwise negative, but as long as you're consistent, it doesn't matter. So yeah, these forces are going to exert a torque, but about what pivot point? Now here's a strange thing. This is an equilibrium, right? So it's not actually pivoting, and strangely enough, because of that, you could pick a pivot point anywhere you want. Now you might say, well, in this problem it has to pivot at the hinge. This is the only place where it sort of can rotate. True in real life, but if you pick, first off, if you pick the hinge as the pivot, which you're more than welcome to do if it helps you solve the problem more efficiently, then these two forces don't exert a torque. Why not? Because the r, the distance from the pivot point, is 0. So the weight exerts a torque and the two tensions exert a torque. But so now let's say we shift the pivot point here. So now suddenly the weight no longer exerts a torque because it's right at the pivot point and r is 0. But then these two forces now exert a torque. And so it turns out that as long as you pick the pivot point at a certain spot, well, how do I want to say it? Like, because you change the pivot point doesn't change the problem. Like, something has to compensate for it. And so what compensates here is the fact that mg no longer is part of the net torque equation. Or you could even pick, for some strange reason, which you wouldn't really want to do, pick the pivot point way out here. So then you may say, well, all the forces now exerted torque. But what changed? What changed was the r, the distance to each force. So that's going to change the torque. Anyway, long story short, no matter where you pick the pivot point, things will change. Parts of this will change, either the r's or the f's, whether or not they exist in that particular what do I want to say? The particular maybe arrangement. So the particular arrangement, things will change. Whatever. You get what I'm saying, I hope. If not, just ask me in person. I might be able to think of it better. But anyway, the choice of a pivot point doesn't change the torque equation. So, for example, let's say we pick here as a pivot point. Now, this is a good place to mention some strategies. I'll mention more strategies when I actually do sample problems. But we want, in this problem, it looks like we'd want to find force 1 and force 2, right? So, a couple strategies. One is, you may think, well, maybe we shouldn't pick the pivot point at one of these, because if we do, then the torque for that point. So let's say we pick the pivot point at F1. Now F1 is not going to be in our net torque equation because it doesn't exert torque at that pivot point. So you might say we shouldn't pick it here because we need that variable to solve for it. You might also say, well, if we do pick it here, then if we don't pick it here, then we have too many variables and we might not be able to solve for it. So it's sort of a, you'll get used to it. You know, you'll get an intuition eventually as to where to best pick the pivot point. And if you don't, the worst that can happen is you pick it somewhere and you realize, this is not allowing me to solve. Let me try a different pivot point. It's not a big deal if you pick the wrong pivot point. Just try a different one. And so, yeah, so let's say we pick the pivot point here. What would the net torque equation look like? So you'd say F torque net equals 0 because it's in equilibrium. And so let me just erase this so I don't get confused. So we're picking 10 as our pivot. So now let's do the clockwise torques because those are positive. So this is going to rotate it clockwise, right? So we got 20 times, remember torque is R times F. So ignore the perpendicular for now. That's going to be important for this one. But in here it doesn't matter because it already is perpendicular. So it's a distance of 4d from the pivot. This doesn't exert a torque, so we'll just leave that alone. This exerts a clockwise torque. As you should be able to see, it's going to wrap it around that way. So plus F1 times 2d, it's a distance of 2d away, plus 30 times 3d. See that this is going to rotate it clockwise, and it's 3d from the pivot, minus, I hope this is still in the video, it might be right at the very bottom, minus F2 times 4d. I did minus because F2 is going to rotate it that way counterclockwise, and it's a distance 2, 3, 4d away. So that's our net torque equation. And you can probably see what this is leading to. System of equations. Right? And so with a system of equations, if you have two equations, then the most unknowns you can have is 2. And so that's going to help guide you in picking a pivot point. We have two unknowns here, right? F1 and F2. So that could work. We could leave these as in our torque equation and then still be able to solve for them with the net force, because we have F1 and F2 here and here and here and here, but we have two equations that can take care of that. If we had three unknowns, like an F3, we would need a third equation to solve for that, so keep that in mind. Now, when you have a problem like this where things are at angles and you need an x and y when you need x and y net force equations, you could potentially have three unknowns, first of all, because you have three equations with which to take care of those in your system of equations. But the thing I really want to talk about, nothing is different over here. You're going to have f net x, where this, let's say let's define direction here. Plus, minus, left and right, plus, minus. So in the x direction, you're going to have fh, which is positive, minus tc equals 0. In your net force y equation, you're going to have up is positive, so you're going to have fv minus mg minus tr equals 0. And then for your torque, well, it depends on what force you're trying to find. The problem may be asking for tc. In that case, you probably don't want to pick your pivot point here, because that's going to get rid of tc in your torque equation. So really you have three options, here, here, or here, and whichever one you pick is going to, again, depend on what the problem's asking. But let's talk about this torque equals r perpendicular f first, and then I'll stop this video and do some sample problems to make all this more clear. So let's say we pick this is our pivot point right here, so let's erase these two. Alright, then let's do a couple of these. So what's the torque exerted by TC? So the torque is going to equal r perpendicular times TC. So this is going to exert a torque, as you can see, counterclockwise, so we could call that negative. But what is r perpendicular? Well, it is the perpendicular distance to the pivot point. So what you do is you see that you take the force vector, which hopefully you've drawn, you go to where it exerts, where the force actually is exerted on the beam or the object, which is right here, and perpendicular to this is either up or down, but the pivot point is down relative to that, so you basically just go straight down perpendicular. See how this line, this vertical line, is perpendicular to that? And so your r perpendicular is the length of this line right here. So you could use this angle, in this triangle to figure that out. What about TR? Well, torque due to TR, again you do r perpendicular TR. What's the r for this one? Well, TR is exerted here at the end of the rod, or the beam, and the perpendicular distance to the pivot point from TR is this way. So perpendicular, right? And you go all the way until you hit the pivot. Yep. Oops, stop. The pivot is right here, so you stop here. And the distance r perpendicular to TR is this distance. Alright, let's do one more and I'll stop the video. What about the perpendicular distance to mg? This one. Well, mg is vertical, right? And it acts right here. So perpendicular is going to be horizontal. And so what we do is we go from where the force is exerted, right here at the center of mass, because weight always acts at the center of mass. And we go perpendicular, and we stop as soon as we reach where the pivot is, in line with the pivot. Stop right here, because that's where the pivot is. And so the distance, r perpendicular here, would be this distance. And again, you got a triangle here, you know this angle, because it's 90 minus that. Pretty easy to figure out. Alright, so I'm going to stop there, and then if any of this is unclear, you can re-watch it, ask questions, or watch the sample problems. I'll do a few, 2 or 3 maybe, maybe more if necessary, and you'll see these in action for real, for reals. Alright, see you later.